Hi everyone, hope you all are doing good. Today I am back with another new video that is on synthesis. Previously we have discussed on the inputs required for synthesis. If you haven't watched that video yet, you can click on this link above. Also I'll share this link on the description box. So in this video I am going to discuss about the synthesis flow. So without any further delay, let's get started. So previously I have discussed about what is synthesis and the types of synthesis. So let's have a quick reminder that. So synthesis is a process of converting RTL codes, those are written in HTL like Verilog or VHDL, into a get level netlist. And there are two types of synthesis, logic synthesis and physical synthesis. So to perform physical synthesis, we must have a logic synthesis. So that's like a logic synthesis is a compulsory synthesis to perform. And based on that only, with certain additional inputs, we can perform physical synthesis. We will discuss about the advantage of physical synthesis and also we'll discuss on the each of the flows. So basically the flow will be common as logic synthesis, only certain inputs will is the difference between logic and physical synthesis, and then comes the advantage of that. So we'll discuss on that. Let's now start on logic synthesis flow. So previously we have discussed more deeper into the inputs. So this time I'm not going to speak much on the inputs. Here you can see two different inputs like MMMC and SPEF file. So these two inputs I will make separate separate video on these two inputs. But other inputs I have already discussed on the previous video. If you haven't yet watched, please go and watch that. So first we are going to see what are the compulsory inputs for this logic synthesis flow. So the compulsory inputs for this logic synthesis flow are RTL, HTC, UPF, MMMC, timing library and TLU plus. These are the blue ones are the compulsory inputs for logic synthesis flow. So basically uh, previously we never previously we used to skip sometimes UPF, we used to skip MMMC, but now these two also become with the advanced technology nodes, these two also become a compulsory inputs. So RTL, as we know, this contains all the circuitry definitions and all the module definitions, ports, pins definitions. SDC contains the constraint files. So it contains all the constraints related to timing, power, then PVT corners, design rule constraints. Everything will be there. Then comes power domain informations, different voltage informations, supply port, nets, all these, all the low power design cells, all these informations will be given in the UPF. Then comes MMMC, which contains all the scenarios. Basically it contains the delay corners and the constraint modes things. So all these informations will be given in the MMC file to analyze, to get analysis views. And then we'll have a timing library, or we call as logical library, for the standard cell and macros. So all the timing, power informations, all these informations will be given there. Then comes the TLU plus. So it basically comes along with timing library. This TLU plus contains, it basically helps us in synthesis to get to estimate RC values. So it contains WLM. So there will be certain lookup table. So based on that, the tool estimates RC values, because in synthesis stage we don't see the placement and routing is not yet done. So that's why we need to estimate the RC values. So those informations will be given on this TLU plus file. So with these inputs, we are going to start this logic synthesis flow. So the first stage is import stage. So here we import RTL MMMC file. These two files we import here, and then we go for elaboration. So at elaboration stage, by that time we need to also import library files. So it will elaborate the design, and then we import constraints and UPF. Then we do the compilation stage. Then we go for optimization, and after that we insert DFT. So DFT means we insert the scan chains. So those are required to check if there are any faults, if there can be any faults or faults during manufacturing. So there are certain testing process to check that. And then finally we get synthesis output, that is we get netlist, and along with that certain other outputs also we get. So we'll discuss on this each of the stages separately. So we know that from Cadence toolset, we have a famous tool that is Genus for synthesis flow. So this is a common and the most popular tool that we use in the industry. So Genus we use from Cadence toolset. From Synopsys we use DC, that is design compiler. But in this video we are going to discuss mostly on Genus synthesis flow. So this is the flow of Genus. So here first, as we can see, it will read like we have to make a setup file. So in that file we have to source all the libraries and the MMMC file. Then we have to source the RTL files. So there are the comments like read library, read leaves to read all the libraries, then read MMMC to read all the MMMC like analysis views, everything will be given on that file. Then comes RTL files. So list of RTL files we have to source by using a command read HDL. Then we have to elaborate the design. Then we'll initialize the design. So whenever we are using MMMC file, that means we have to initialize the design. For that we use init design. And then we import constraint files along with a UPF file. So for that, for constraint file we use read SDC, and for UPF we can just source the UPF file directly into the setup file. And then we will go for generic synthesis, that is scene generic, mapping, that is scene map, optimization, scene opt, and then finally we'll generate the we'll analyze and we'll generate the reports, and we'll see from the output files whether the constraints are met or not. So whatever constraints are given on the HDC file, whether those are met or not. If yes, then we will hand over the netlist and the database along with the HDC to the PNR team, to the physical design team, to perform place and route. If the constraints are not met, then again we have to modify the optimization modify the optimization directives. Those are like whatever constraints are there, maybe sometimes we have to relax little constraints, or we have to add some more constraints in the SDC file. So like that this flow works basically. So now we are going to see what are the major goals for this synthesis, why we perform this synthesis. So the major reason to perform this synthesis is because it allows designers to visualize how the design will appear after manufacturing. So we can get that idea only if we have a gate level netlist at first in our hand. So for physical design engineers, gate level netlist we have to get, because RTL tool is just giving the circuitry descriptions. It basically is giving all the behavioral descriptions in form of program. Like it is telling inputs are these, outputs are these are the wire connections, but those are written in program. But we need to get the gate level connections, and that gate level connection is done by the synthesis tool. And the synthesis tool are also performing optimization to obtain this gate level netlist. So there are certain optimization also we go for, because we know in the industry nowadays there is a big trade-off is going on, PPA, that is power, performance and area. So maintaining three of them, optimizing three of them parallelly is really a challenging task, but parallelly we have to do that, and tools are also coming with very advanced algorithms. And also we are seeing that we can also, if manually, designers can perform certain optimization by giving certain inputs. So the optimization that we do at synthesis stage are power optimization, logic optimization, congestion aware optimization, timing aware optimization, area optimization. Then we insert the DFT logic, that is the scan chains, and finally we check that whatever the logic was given on the RTL should match with the netlist. So basically we are maintaining the logic equivalence between RTL and netlist. So this is a mandatory thing, because functionality should remain same, the logic should remain same, logic should not get affected because of any optimization. So these are the major goals of synthesis. Now let's start logic synthesis flow. So first is import stage. So at import stage we create a setup file where we read all the RTL files, MMC file and the libraries. So as we know that RTL files means it contains all the modules, port, pins, instances and their connection information. So it basically represents the circuitry behavioral information. So basically it captures the desired behavior of the design. And then we read MMC file. So MMC file basically helps to generate analysis views based on different delay corners and constraint modes. So these MMC files basically helps us to perform like survive this chip even in different voltage, different with different temperature. So we will have to give more information on this file, and based on that the tool will try to optimize, tool will try to perform, tool will try to see like whether it can perform better results. And there will be libraries also. So from the libraries, so libraries are based on standard cell and the macros. So from there we'll get the timing info of standard cell and macros, then power info, then PVT conditions, also the functionality. So timing info like DRVs, all the design rule violation checks will informations will be given there, like max transition, max capacitance, max fan out, max length, all these informations will be given there. Then setup and hold time, delay informations, recovery and removal timing, all these informations will be given there. Then the power related like leakage and internal power information will be given there. PVT conditions will be mentioned there. Also the functionality information like unitness, we already discussed about unitness. If you haven't yet watched that video, you can click on the link here. I'll share the link also on the description box. So unitness is also is very much compulsory, because unitness means it basically talks about how like whatever input, whatever transition happening on the input, how it is going to affect on the output. So based on that we need to also aware about this functionality. So these are the inputs required, and if any of the file is missing, or if any module is module or pins or ports are instantiated in the file, in the RTL file, but not properly defined, or proper for those proper module, proper RTL files are not available, that time we may see empty module issues or linking error or unresolved references. So basically empty modules comes only if the module doesn't have complete input, complete definitions like complete input, whereas output, all these definitions are not properly present. That time we say it's an empty module, because it has instantiated the module name but it hasn't defined properly. That's why it's an empty module, it doesn't have any content inside it. So it can happen like while we start with the synthesis flow, that time still probably the RTL team, the design team is still making the RTL files. So probably they have just instantiated and they have just hand over to us so that we don't waste our time. So that time we may see certain empty module getting reported in the log file. So we have to analyze it from the log file, and if we see such empty modules, and if we have to discuss with the design team like whether we need to preserve it or not. If we have to preserve it for future reference, then we have to set it as set don't touch in the constraint file. Otherwise the tool will automatically optimize them. That means tool will automatically remove these empty modules if they can't find proper definitions. And if certain library file is missing, or if we see any module pins or ports are instantiated but not defined properly, that means if any of the RTL files are missing through like maybe somewhere it is mentioning the module name but it is not sourcing, that it can't link to that file basically, because that file is not present in your directory, or probably some mismatch is happening between the RTL files. That is the time we face this linking error or unresolved references. Next is elaborate stage. So in elaborate, the first and the foremost stage is it basically convert all the RTL codes into a generic technology library. So basically there is a generic technology library which contains basic logic gates and flops, and these are generic means these are technology independent. They are not dependent on any technology. They are not dependent on any nodes. So when we don't have target based technology libraries ready in our hand, we go with this generic level technology. So it's not a compulsory stage, but people generally go with this flow till the time we have all the inputs properly constrained in our hand. Now, that is the time we generally go for this pre-mapping stage, and this generic stage is the pre-mapping stage, and we go for scene generic by to perform this generic stage, and it converts all the codes into a GTAC library. So it basically converts all the codes into respective, it basically convert each and every instances to the equivalent module definitions, to equivalent logic gates and flops, and it basically infers the registers and muxes and also the clock gates. So if passage or negate is mentioned in any of the code, that means it is basically representing representing a flip-flop structure. So at elaborate stage, tool will convert those passage negates, that code, those modules, into a flip-flop or latches. And if else statements are there, means it basically will infer a mux to convert those if else statement. So like that it infers registers and mux. And then also, if there are any date codes, if there are any date codes in the design, that means if certain date codes means if there are any unloaded output, so this date code removal means it will remove those unloaded output. So it basically see if there are any unloaded output from the RTL file, then it will optimize those codes. So that is why it is called date code removal, because the unloaded output means that code is not valuable. That's why tool will optimize those codes. So if any of the, again, if any of the module or library is missing, we may get linking error or unresolved references. Even at elaborate stage it will check. So finally, after that, we'll import the SDC file. So SDC file, as we know, the timing constraints, it basically have the timing constraints such as clock definitions, clock frequency, clock period. From clock period, we'll get the clock frequency information, driver constraints, design constraints like max trans, max capacitance, then WLM informations. All these will be imported from the SDC file to optimize the netlist. So now here comes a question like, can we do synthesis without timing constraints? And the answer is yes, it is possible to do synthesis without giving timing constraints. However, the resulting design may not meet the timing requirements of the design. The timing constraints are used by the synthesis tool to ensure that the design meets its timing requirements, right? So timing constraints specify the maximum delay that is allowed for each path in the design. So without timing constraints, the design may not meet its timing requirements. The design may be slower than expected, because if you are not mentioning the maximum delay, it will obviously be slower than the expected. That means again, the performance wise it is failing. The design may consume more power than expected if you are not properly mentioning the power constraints. And again, the design may be less reliable. That's why we prefer to have a constraint file as a compulsory input for synthesis tool. Then we have to source UPF file. So UPF file we need only when we have multiple power domains in the design. So multiple power domains means UPF file will contain all the power domain informations, that there will be different domains which will operate at different power and different voltages, and their supply ports, net definition, supply side definition, then all the low power related cell definition like retention cell, level shifter, isolation cell, all these all these strategies will be mentioned in the UPF. Then at elaborate stage, at the end of elaborate stage, the tool performs logic optimization. So logic optimization means it basically removes the flops with constant value. If it is having logic 0 as constant or logic 1 as constant, it will remove those flops. It will remove the unused cells or where in the design. It will also try to detect if there are any identical cell. Then it will report like, okay, we are finding some identical cells. So another major functionality of this elaborate stage is to uniquify the design. So I forgot to mention that here. So tool basically uniquify the design. Uniquify means it basically try to find the design is containing all the unique instances and modules, unique instances basically. So that's why it detect if there are any identical cells or nets or ports or pins. So it will throw some errors, and then we have to see if those are identical. We have to mark those with, like, let's say there are two pin names are there of same or two net names are there, two of same name. So we have to make it like _1 _2. like for an example I'm just giving, just to make it unique, just to make both identified separately. Otherwise if we are applying constraints, it won't affect, like both won't get proper constraints. That's why we need to have a unique instances or cells. That's why during logic optimization, a tool also detect identical cells and automatically it throws an error if it finds any identical cells in the design. Next is compile stage. So compile stage basically, at compile stage we perform the technology mapping. So at elaborate stage we perform the generic mapping. At compile stage we are doing technology mapping. So for that we have to use the command scene map. So basically whatever cells now we have in generic, whatever generic cells we are having now from elaborate stage, now those cells will be converted into the targeted technology gates. That means for whatever technology node we are working, for those for that particular technology node we have certain libraries, and those libraries we already taken as an input. So for that library it will directly convert it. It will directly it will convert the generic cells to generic gates to target based gates to meet the timing constraints, to have an optimized to have an optimized, more optimized, in order to meet the timing constraints. And this target technology gates contains area, power and timing related informations which are already present in the library file. So here at this stage we see the clock gating insertion. So as we convert all the generic cells to the target based cells, we try to see, like, clock gating means, I'll make a separate video on clock gating as well. So clock gating means previously we used to have only one AND gate, but now we are using a lot of different form of clock gating cells. There can be sometimes mux can be used as a clock gates, and also in the library file we'll have a separate set of clock gates, integrated clock gating cells, which we say, that is ICGs. So there will be a latch connected to a AND gate. So that kind of code is already written on the RTL file, and based on that generic gates are already converted, and on from generic gates those informations will convert it to the target based gates. Now this will actually represent the clock gating. So at compile stage we are getting the clock gating insertion, proper clock gating insertion based on the target technology nodes, and also the low power cell insertion will be there. So whatever we are mentioning on the UPF file, like isolation cells, level shifters, retention cells, based on that based on that synthesis tool will insert this kind of cells. And also, and these all cells are already mentioned in the library file, all these cells are there on the library file. So from the library file it will take all these cells, and it will just convert, it will just map into the target based technologies. Target based technologies means it basically contains all the target based constraints. That's only, like, timing proper targeted constraints are mentioned. So based on that those are now getting converted, and then again it will perform a logical optimization, and again it will go for incremental optimization. So next is an optimization. So tool performs an optimization, that is scene optimization. So this basically happens whenever, so this optimization is done in order to have proper timing met, proper power met, and also to meet the area constraints. So to achieve optimal PPA we go for this synthesis stage, we would go for this optimization stage. So this optimization requires, like, sometimes we may need to swap VT cells, there will be certain threshold voltage cells, we may need to change the drive strength of cells, we may need to restructure the logics, like we can level down the logics to like with same functionality, by mentioning the same functionality we can level down the logics, we can restructure the logic with lesser levels, like instead of 3 gates we can have same functionality with 2 gates. So we can restructure a logic to optimize the area, and also to optimize the design. Then also we have to we can do buffering and cloning based on the constraints to achieve the optimal PPA. So now we have to insert DFT. So design for testability. So DFT is basically, it helps in detecting manufacturing defects using certain test input vectors by inserting scan chains in the design. So these DFTs are used for testing each and every node in the design in order to test stuck at false, and also so that we don't mention we don't see any issue during manufacturing time related to delay. And also by having scan chains, the design can be more controllable and observable. That's why we go for this stage. And after scan chain insertion, we go for a last but the incremental optimization. So here the tool further see, like after scan chain insertion, if any further new violation happened or not, if any errors are coming or not, if there are any critical paths coming or not, any timing violation are happening or not, it just want to check, and that's why it will optimize further to get a optimal get level netlist. So the final output from this logic synthesis flow will be the optimized get level netlist, SDC file, the scan def, and the reports. So there will be multiple reports related to area, timing, power, all these informations will be given based on the QR, basically the quality of result. Based on that, there will be multiple reports for each stage of the synthesis design. For the each stage, it will generate reports, and these are the outputs we have to hand over to the physical design team, who are going to perform place and route based on this. So scan diff basically contains the scan chain informations, so that's why you also need the scan diff. So diff means it basically contains all the definitions of all the scan related informations. Next is physical synthesis. So for physical synthesis, we require inputs same as logical synthesis, but there will be three additional inputs. Those are spef file. So spef file is basically so basically first we need the floor plan, first we need the physical library and technology file. So this physical library and technology file, these are the physical info, they contain the physical information. So physical libraries basically we call as standard cell libraries. So it contains all the abstract view of cells and macros, blockages, pin, etc. All these definitions will be given there related to standard cells and macros. And TechLef basically contains all the geometry, boundary, metal layer information, VI information, pin related informations related to width, pitch, dimension. All these informations will be given in the TechLef file. So this based on this information, we feed we whatever output we have got in the logic synthesis flow, this output along with this physical library and technology file, we will give to the PNR team. That is for floor planning. Floor planning is the first stage of physical design. So for floor planning, these are the inputs required, must require inputs. Except spef file, except this spef file and the floor plan diff file, rest all other inputs along with this output file of logic synthesis are the inputs for physical design. Now the first round of physical design we will perform till floor planning only. We'll have a floor plan, we'll place all the macros, blockages, we'll place all the IO ports, pins, the basic physical cells we'll place, the initial placement basically we'll do. Then we'll sometimes depending on the design, some companies prefer to have initial placement information into a dev file, and some people also like to have final placement of cells, and then they generate a dev file, and then again they give that file to the synthesis tool. But both are okay for it. So we basically generate floor plan diff. So there in initial placement of macros and standard cells information will be there. Nowadays we are mostly going for the placement stage also, till placement stage we are going, and we are seeing like till placement stage whatever the congestion is coming basically. So whatever congestion informations are coming, based on that whatever informations we are getting, we basically generate a diff file. On that we write out into a diff file, and that diff file, along with that we also extract spef file. So spef file is basically gives us the extracted parasitic RC information. So till placement stage we will have already power nets routed. So pre-routing was already done. So with that pre-routing stage, we can expect what are the already like what is the congestion and how much whatever reserved routing tracks are already there for signal and clock net routing. So we can have that estimation basically here, and also we are getting certain RC parasitic information till placement stage. With that information, we are going to feed into the synthesis tool again. So physical synthesis is basically we are performing logical synthesis plus we are performing the first level of floor plan plus placement in the physical design, and whatever output we are getting at placement stage in form of def, we will feed those output in form of def file. We'll generate a def file and a spef file, and then again this spef file, physical library and technology file, and the floor plan def, these three files will feed into the logic synthesis. So we'll give into the synthesis tool basically. Now since we are giving the physical information, so it won't perform the logical synthesis anymore, it will perform the physical synthesis. When we don't have physical information, it performs logical synthesis. When we have physical information, it performs physical synthesis. So this is what physical synthesis is all about. So the reason why we go for this physical synthesis is that at advanced nodes we are seeing that after placement and routing, the physical effects with long widths are coming, that is more delays are coming, more voltage drop is happening because of this parasitic RC and because of this parasitic effects, and this is causing a difference in physical and logical version. That means whatever netlist we are getting, the netlist and the layout, they are having not logical equivalence. For that only we are going for this physical synthesis, because we have to maintain the logic, we have to make a correlation between this physical design and synthesis. But due to lot of physical effects because of these long wires, we are facing this issue. That's why if we are having this congestion information and the placement of standard cell and macro information, we can easily, the synthesis tool can easily further optimize the design in such a way that it can have a better correlation with the physical design tool. That's why with floor plan def, better correlation between synthesis and PNR is seen, and also better turnaround time, because to fix again to have a logical equivalence between synthesis and physical design, it's very tough. We have to go for multiple rounds of iterations, and it's a very time taking. So because runtime will be more, time is taking more, so instead of like it will take more time to finish a project itself. That's why to save time and to have a better turnaround time, that is to save time and to have only one iteration, if we can get better result, why we will go for multiple iterations, right? That's why we are going for this stage, and also it is giving us better PPA optimization design, optimized design. So this is the advantage of physical synthesis. So the output from physical synthesis will be optimized get level netlist, SDC, scanDef, reports, def file, MMMC file. Now these are the outputs, and finally with these outputs we will now start the full physical design properly now. Now when we'll start full physical design, we'll see there is a better correlation, that we won't see much issue at placement stage, we won't see much congestion, because it is performing a congestion aware as well as timing aware synthesis. Physical synthesis is better for congestion aware and timing aware. That's why we go for this physical synthesis. So this is up to this about this logical and physical synthesis. Hope you all understand this. If you have any doubts, you can comment down on my video. So on the upcoming video, I'll try to make a video on the checks to do after synthesis. We have to perform certain checks after synthesis. We'll make a video on that. The timing analysis after synthesis. Then we have to understand the each and every reports after synthesis. We have to analyze and understand the reports and how can we optimize them further. So we will make a further video on these three topics. So if you really found this video valuable and informative, please do hit like on this video, and if you haven't yet subscribed to my channel, please do hit subscribe. Don't forget to press the bell icon so that whenever I'll upload another new video, you can get the update immediately, and also share it with your friends, colleagues and VLSI aspirants. Thanks for watching this video.